In this set of lecture notes, we're finally going to start talking about forces. So I've kind of mentioned forces a few times, right? We never did anything else with them, and I kept telling you we're going to keep postponing, so now is the time to do it. So let's start with the simplest definition of a force. A force is, in very simple term, is defined as a push or a pull. So in these terms, you can explain what a force means to anybody, including your 4-year-old nephew. So anybody can understand that. If you want something a little bit more scientific, then you can say, you can say quite a few things. So first of all, you can define it as external influence on an object. I'll talk about external in just a minute. You can say something like a force is always exerted by an agent. So that means there has to be something or someone exerting that push or pull. It doesn't just exist out of nowhere. Okay? And you can also say that forces are vectors, as in there is a magnitude and direction. So we're coming back to usage of vectors. Okay. So there's quite a few things that you can say. Now, as far as external and internal is concerned, so we're studying mostly mechanics in this class for the great majority of the semester. So we only talk about external forces in mechanics. External as in external to an object or a body that we're interested in. There are internal forces as well. For example, all of your atoms and molecules that make up your body, those are held together by forces. But those forces are internal to your body. So if we're talking about what your body or a human body can do, walk, move, drive, blink, and so on. Whatever's happening with that body, we're pretty much disregarding what's going on in the body, inside the body. We're only talking about what's going on with the influences from the outside. And the same thing goes for all the other objects. Balls, houses, horses, cars, whatever, right? So we're pretty much not going to deal with internal forces in this class. We're only dealing with external forces. External forces can be separated into two large categories. There are contact forces and non-contact forces. Non-contact forces are also known as long-range forces. So let's start with these first. Non-contact, also known as long-range forces. So these are forces that an object feels without coming in direct physical contact with another object. There is only a handful of non-contact forces. Gravitational. We're definitely going to talk about that in detail in several different places. Electric, magnetic. So these two forces are discussed in great detail in the second semester of the course. Okay. There are also what's called weak forces and strong forces. Okay. So the terms weak and strong can be a little bit misleading because in general those terms describe the strength or the magnitude of the force. But also those forces, sometimes strong force specifically is referred to as strong nuclear force, and weak force, that one's kind of goofy. So anyway, strong nuclear force is also described during second semester or third semester of physics when we talk about nuclear interactions. A weak force is typically not discussed in general physics. So weak force is something that exists between very particular classes of particles, very specific classes of particles that again are not generally discussed in general physics. So we're not going to have to worry about that. Now, electric and magnetic force are often combined into a single force. That would be electromagnetic force. It's all basically part of the same phenomenon. We're not going to worry about it right now, but next semester we will. So basically there are 4 non-contact forces: gravitational, electromagnetic, strong force, and weak force. The rest of forces, anything else you can think of, are going to be contact. So contact forces literally happen when the 2 objects touch each other, right? So when they come in direct physical contact. And by the way, when I say object, I really mean anything. So for the purposes of discussion of forces, even things like animals and people, we're still going to consider them quote-unquote objects. Okay, so when any object comes in contact, touches another object, that's when contact forces happen. And I bet you already know quite a few of these. So let's write down a few. There are a lot of them. So let's just write down a few. For example, we can talk about friction. I'm sure you've heard that term before. Drag, aka resistance. You probably have heard the term air resistance, but the term drag is a little bit more general than that. We'll get to that when the time comes. Support forces. So one of the types of support forces is called the normal force, and that one we'll discuss a little bit later in a few minutes. Let's see. What else can we think of? Spring forces. That one also is coming later during the semester. Buoyancy. I'm sure you've heard that term before as well. And so on. So there are quite a few more types that we can discuss and classify. So throughout the course of the semester, we'll deal with all of this. Plus, there are just general, I probably shouldn't have put ... just yet. There are general forces that don't fall into any one of these categories, but we can just say push or pull by a person or an object. Okay, so like for example, if 2 people shake hands, they exert forces on each other. We'll come back to that. So this is where I'm going to say ... There are quite a few of those. Okay, so we're going to concentrate on forces for a long period of time in this course. And even when we move on to other topics, we're still going to keep bringing forces into the mix, because a lot of mechanics revolves around knowing what forces are and what forces do. So then, another thing, I already said this in general, but I'm going to write this again. Forces are vectors. So they have magnitude and direction, right? That means I can write a force like this with a vector arrow, and I can write it in terms of components. So force is going to have x and y components. By the way, that's what we're using to denote any force, is capital F. Okay, so any generic force. And then I'll show you in a minute how we can distinguish between different forces. So any generic force can be written as vector F. It can be written in terms of components using angle brackets. It can be written in terms of unit vectors. It can also be written as magnitude at angle theta, right? So if you're specifying magnitude and direction, right? Of course, you already know everything about vectors in terms of how to find magnitude and direction if you have components. So this should not be anything new. You already know this. I'm not even going to box it because this applies to any vector, right? You already know how to find direction from components using inverse tangent. And you already know how to go the other way, how to find components if you have magnitude and direction. And of course, you need to remember about reference angles, right? And you need to remember that little trick about inverse tangent as well. So everything that we learn about forces is going to apply in this case. And as a rule, there are going to be some exceptions, but as a rule, we're still using the standard coordinate plane. So positive is to the right and up, and negative is to the left and down. So everything that you know about vectors is going to be applicable for forces. So, for example, if I have something like this, let's say I have three forces, F1, F2, F3. I could ask you to take these forces. Of course, I would have to give you a bit more information. I would ask you to add these forces together, right? So like you could do graphical addition. I'm not being very careful here. Obviously, you can do a better job, but I'm just reminding you, right? So you could have a resultant force. I'll talk about that in a few minutes too. So you can do this graphically. You can also find all the x components, obviously paying attention to positive and negative, right? You can also find all the y components, again paying attention to positive and negative. And you can add the x components separately. I can call this the net force. In fact, let me write it like this. F net x, right? I can add all the y components separately, right? Get the y component and then proceed to finding magnitude and direction. Remember again that one of the most important pieces of information about vectors in general is that x and y directions or components are always treated separately and independently. So same thing applies to forces. You're always going to deal with x components first, or separate, and then y components separate, and then whatever these forces do is going to be separate in the x direction and separate in the y direction. Let's talk about units of force. Units of force, any force, are called newtons. So denoted by capital N, Newton. Again, we discussed this briefly, but if you're writing out the name of the unit, you're going to write it with starting with a small letter. This unit is named after a person, Isaac Newton. We're going to talk about him in a minute as well. So Isaac Newton is considered the father of not just physics, modern physics, but also calculus. So we commemorate him by naming the unit of the force Newton. So not capitalized when you write the unit, obviously capitalized when you write his name, and capital N is how it's abbreviated. Now, in the very beginning of this semester, we talked about derived units. So a Newton is a derived unit. And the definition of a Newton is kilogram times meter per second squared. So all of those three generic base units that we discussed, the fundamental units that I've told you about, unit of mass, unit of length, and unit of time, they're all combined together to give us the unit of Newton. So every time that you do a calculation of some kind using those units and an equation that I'll show you in a minute, and you get that particular combination, you know to change that combination to newtons, just like with all the other derived units that we're going to see in this class. Now, what are the units? What are these units for? Kilograms are obviously the units for mass, and meters per second are obviously the units for acceleration. So forces are related to masses and acceleration. Some of you may have seen this equation in high school. Force equals mass times acceleration. Well, we're no longer in high school, so I'm going to say that this equation, the way it's written, is wrong. And I will come back to it in just a minute and tell you what is the correct way of writing this equation. But before we do that, we also need to talk about mass and weight. Okay? So let's do that, actually more specifically about mass, because we use that quite a bit when we discuss forces. So mass is defined as amount of quote-unquote stuff. Very scientific, right? So what I mean by that is that mass essentially is related to what the object is made of. So how many atoms, how many molecules, what kinds of molecules, and so on. Luckily for us, we don't have to talk about that makeup of an object in this class. We do that a lot in chemistry, not in beginning physics. We'll talk a little bit about that when we get to gases, but not much. Anyway, so that's what mass is. Mass is the amount of stuff. And of course, this you already know, that mass is measured in kilograms. Not to be confused with weight. In everyday English and quite a few other languages, these two terms are used almost interchangeably. In physics, they should not be used interchangeably. So weight, the formal definition of weight, is the strength of gravitational attraction. Notice how I didn't say that weight is the same thing as gravity. It's not. It's the strength of gravitational attraction. It's basically a measure of how much the Earth pulls on you. The two quantities, mass and weight, are related, but they're not the same. So the other name for weight is force of gravity. And again, please do not call it just gravity. Gravity is a really large phenomenon, we already talked about that involves all kinds of stuff, including stars and black holes and light traveling through space and all kinds of other things. So it's a really big phenomenon. Force of gravity is something that we can define very simply. So weight and force of gravity are the same thing. You can use little w, not big W, that's something else, but you can use little w for weight. I typically don't. I typically use this notation, F with a subscript little g. Specifically little g. I'll tell you about big G later. So that's how I denote all the forces, capital F, and then a subscript to tell us what kind of a force this is. So weight is the same thing as force of gravity, and it's defined as mass times acceleration of gravity. Right? Now remember, G is 9.80 meters per second squared at, on, or near the surface of the Earth. We're going to learn soon how to find that value elsewhere, not on surface of Earth. For now, this is what we're using, right? So if you take that value and multiply by the mass, you will get force of gravity that the Earth exerts on an object. So Again, you have to be really careful and really nail down all these differences. There is force of gravity, aka weight. There is mass, and there is gravitational acceleration. Do not confuse those three quantities. Very different. Now see the units here, meters per second squared, right? So this is what I get, kilograms times meters per second squared, right? So that's how I can define units of newtons in the simplest way. Okay. So we're going to be using both of these quantities. So force of gravity is one type that we're considering. Since I'm talking about types of forces, let me show you a couple more different kinds of forces that come up all the time. Normal force. I already mentioned it, but I didn't define it just yet. So normal force is the support force exerted on an object by a solid surface. Keyword solid. Okay, so when we talk about liquids and gases, something else starts happening. We'll come back to that. So right now we're talking about solid surfaces. The word normal here is actually a mathematical term. Normal in math means perpendicular. So normal force is always perpendicular to that solid surface. So for example, if I have an object sitting on the floor, the normal force exerted by that floor on the object is going to be perpendicular to the floor. By the way, that's the notation for it. F with a subscript capital N. Sometimes people just write N or even N. So that's confusing because N is in Newton and then little n just means way too many other things. So please stick with that notation, F with a subscript N. Okay, let's draw a couple more here. So if an object is sitting on a slanted surface, this normal force is still perpendicular to the surface. And I can do this at any angle. So here is the surface, here is the object. So you are going to be drawing normal force always perpendicular to that surface. And even if I have something like a ceiling, like, I don't know, lamp fixture attached to the ceiling, this is not going to be much of a support, but I would still draw normal force as perpendicular to that ceiling. So whenever an object is in contact with a solid surface, so there has to be a physical contact there, that force is always perpendicular to that solid surface. Another force that is worth mentioning here is force of friction. That one I'm sure you've heard before. So force of friction is defined as opposing, I'm going to put motion in quotation marks. In a minute I'll tell you why. Sometimes people define friction as resistance, not air resistance, but just resistance. Sometimes people even use the term retarding force. There are a few other terms, but force of friction is definitely the most commonly used term. I'm going to use capital F with a subscript little f for force of friction. Sometimes people use just F, little f, but I don't like that because that also means a lot of other things. So please don't do that. And the equation for force of friction is mu times the normal force. First of all, this is a scalar equation. Okay, scalar equation only. This doesn't have anything to do with vectors. Okay, so this is only for magnitude. Mu, it's a Greek letter mu, or maybe like this, mu. Don't call it u, don't write it like this. It's a special symbol, it's a Greek letter, so it has to be written properly. This is called, this mu is called coefficient of friction. It's a unitless quantity. Remember I told you that we are going to see unitless numbers, unitless quantities in this class. So this is one of them. It's just a number, okay? And really, if I'm going to define coefficient of friction, I really should write it like this. Force of friction divided by the normal force. And I'll box it too, even though algebraically this equation is identical to the one above it. But conceptually, this helps us understand what exactly we mean by coefficient of friction. So it's a ratio of two forces that two solid objects, or rather that a solid surface exerts on an object. So I said two forces. Let me draw this picture here. Okay, so here is my box on the surface. We already know that the normal force is going to be pointing up like this and perpendicular to the surface. If the object is moving, then there is going to be a force of friction. Remember, I used the term opposing, and I also used the term retarding. So this is what I mean by both of those terms. So it's a force that acts opposite of motion. And again, I said motion in quotation marks. I'll get back to that. So if an object is moving or even trying to move to the right, force of friction opposes that. Okay? It's along the solid surface. I should write that too. So along the surface. So normal force is perpendicular to the surface. Force of friction is along the surface. So where does this come from? Well, I have this object, right, on a surface. I'm not drawing the details of how those two things are in contact. But if I zoom in into this, I'm not going to just see straight lines, right? If I zoom in into like almost atomic scale, I'm going to see probably something like this. So the two surfaces are not flat. There is a lot of nooks and crannies and jagged pieces. So that just comes from the fact that atoms are not perfectly aligned. This is also kind of a great exaggeration, but you can do sort of something like this, right? So the atoms are not perfectly aligned. It's not easy to make a surface where it would be atomically flat, as in atoms would be perfectly aligned. And it's definitely not something that happens in nature. So those surfaces have all of those jagged parts, right? Nooks and crannies and bumps and so on. And so when you drag an object against a surface, all of those jagged parts and nooks and crannies that kind of get stuck in each other. So this is a lot more over-exaggerated, but it kind of looks like this. So it's almost like a Velcro effect. You try to drag a piece of Velcro along the other side of Velcro, and you see those hooks kind of hooking onto it, right? So that's exactly the same thing that happens between two surfaces. It could be on atomic level, but that's the origin of friction. And of course, because it depends on the surface, it depends on how those atoms and nooks and crannies and jagged edges and so on, how they hook onto each other. That's what determines what mu is. So it depends on two surfaces, two materials even. Only two materials. Okay? So for example, if I have let's say if I'm talking about ice skating, there is very little friction between the metal of the skate and the ice, very little friction, versus something like rubber on concrete, like car wheels. There has to be friction in order for car wheels to turn, otherwise they just slip and slide. So coefficient of friction depends on the two materials. And you can look up, there is a little table in your textbook, or if you want a bigger table, you can look up any number of materials, any combination of materials online, and then figure out what this coefficient of friction is. Typically, there are actually two kinds of coefficients of friction. Typically, you will see that the coefficient of friction ranges from 0 to 1. So mu equals 0, we call that frictionless surface. Okay, so in real life, nothing is ever perfectly frictionless, but in simple physics problems, we can approximate surfaces as frictionless. And you'll see that in problems. You'll see something like assume frictionless surface, right? So then you know there is nothing to worry about there. Again, typically, coefficient of friction ranges from 0 to 1. Could be 0 for frictionless surface. It's never really equal to 1. I shouldn't say never, but for typical materials, like simple typical materials, it's not going to be greater than 1. There are situations where you have some crazy, weird structure, man-made materials that have a coefficient, the combination of the two has a coefficient of friction greater than 1. But typically we don't see that. So I'm just going to leave it at this. I'm going to box this, right? So it's just going to be a number, a decimal, like 0.5 or 0.7. That's between 0 and 1. And notice also two subscripts here. K stands for kinetic friction, aka sliding. And S stands for static friction, as in the object is not moving. But wait, you're gonna say, we just said that friction opposes motion. So how can an object not move and still have friction? Well, here is how. I'm just gonna keep drawing this picture. Let's imagine a box on the floor. And it's not just going to be any floor, it's going to be a fluffy carpet. It's my favorite example. A box or a piece of furniture on a fluffy carpet. So let's say you want to move this box. Okay, so you're going to come in and push. Yes, I know, it's a really horrible picture of a person, but whatever. You're going to push on this box. And you're pushing and pushing and pushing, but the box remains stationary. Okay, why? Because the surface of the box, the bottom surface of the box, and that fuzzy fluffy carpet are doing that Velcro effect, right? So you are pushing to the right, and force of friction is directed to the left. So it opposes the quote-unquote motion. It opposes the direction in which motion would be happening if it was happening. Okay? And then let's say you finally pushed hard enough to where the box is moving, right? So now it's moving at some speed v. You keep pushing it. Okay? So now you should know what I'm talking about here. The force of friction as the box is moving is actually smaller than the force of friction that prevented the box from moving. So this is what I mean by static force of friction and kinetic force of friction. So force of kinetic friction for the same two surfaces is always smaller than force of the static friction for the same two surfaces. It's actually better if I write mu k is smaller than mu s, which I did already. Okay, so basically this means it's harder to get the object to set in motion versus to keep it in motion. If you don't believe me, find a fuzzy carpet or a ground that has dirt and brush and grass and bushes on it, and try to push something like a piece of furniture across that, and you will see that this is the case. Now, force of static friction actually can kind of vary a little bit depending on what's going on. So that's why you have to start pushing and then slowly kind of increase your force of push until you overcome friction. So you may actually see force of static friction be written this way. Instead of an equation, you may see it written as an equality. So the maximum force of static friction would be mu s times normal force. So you kind of have to build up to it. So try that too. Take a piece of furniture on a fuzzy carpet or on the ground or something like that and start pushing. And start with a very small, easy, gentle push. It's not going to move. Then you increase your push. It's not going to move. Increase your push some more. That's when you've reached that maximum amount of static friction. And that's when you're overcoming that maximum amount of static friction. Okay? So I'm not going to box these equations, these two bottom ones, but I still want you to think about what they represent. So you definitely need to be able to tell the difference between the two. Typically, though, we very rarely deal with that situation in terms of problem solving where you have to increase force of friction over time, or increase your push over time to overcome force of friction. So most of the time, if you get a problem that deals with force of friction, it'll just give you mu s and mu k, and you're kind of almost automatically assume that force of friction, the static force of friction, is going to be at the maximum when you have to overcome it. Typically, but not always. Okay? By the way, all of these pictures that I've been drawing here, showing forces, I'm kind of building up to what's called free body diagrams. Or FBDs. So in the next set of lecture notes, I'm going to show you what exactly a free body diagram is and how to construct one. I have to do a couple more things before I build up to that, but I strongly recommend that before the next set of lecture notes that you actually look it up and kind of see if you can take the textbook examples and see what kind of forces are acting within those examples. So that'll be a big help for you to understand free body diagrams. Okay? The last thing that I want to do in this set of lecture notes is to talk about Newton's laws of motion. So I'm just going to define them. There are 3 of them. Okay? And then again, in the next set of lecture notes, we're going to start learning how to utilize these laws of motion for problem solving. Now, they are a little bit, this name, Newton's laws of motion, is a little bit misleading because these laws are actually about forces. Okay? Laws about forces. But that name, Newton's laws of motion, suggests that forces are related to motion. In fact, I'm going to write it over here on the side. Forces are related not to motion. Jeez, I can't write. Related to changes in motion. I'm going to underline that. It must be important, right? Forces are related to changes in motion. What do we call change in motion? Acceleration. So that's what at least the first two of Newton's laws are about. So let's just write them out. This is the only time that I'm going to write out in paragraphs these laws of motion. And like I said, in the next set of lecture notes, we're going to learn how to use them. So, first law. An object at rest remains at rest. An object in motion remains in motion. At constant velocity. Unless acted upon by an external, unbalanced force. An object at rest remains at rest. An object in motion remains in motion at constant velocity, unless acted upon by an external, unbalanced force. We already talked about this word, external. So in this class, we're only considering forces acting from the outside of an object. So exerted by an external agent. Okay. And this word, unbalanced, means that forces don't necessarily come alone. So you could have something like this, which we already kind of briefly looked at that example, right? So if you have, let's say, a bunch of forces acting on an object, you could figure out if these forces balance each other or not. So usually we will write it like this. The symbol you may recognize from math. It's a capital sigma, Greek letter, and it represents sum. So sigma F means sum of all forces. It's exactly the same thing as net force. So it's kind of a grand total of everything. Okay, so what we need to do, if we have a bunch of forces, we have to find sum of all forces. And again, we'll do an actual example of that in the next set of lecture notes. So we do components, add them, blah, blah, blah. So anyway, this external force could be balanced or unbalanced. So if we get sum of all forces equals 0, it means they're balanced. All forces are balanced. It's also known as equilibrium. We'll talk about that too. Okay, and if you get sum of all forces not equal to 0, it means they're unbalanced. So if the forces are balanced, the object does not change its motion. I'll give you a little hint. This means acceleration is 0. Okay, and if the forces are unbalanced, the object changes its motion. This means acceleration is not 0, which, by the way, is actually Newton's second law. So first law just kind of goes up to here. Okay. This law is also called law of inertia. Okay. And then we can define inertia as resistance to changes in motion. Okay, so my favorite example to illustrate that is, let's say you're standing on a bus, the bus is moving forward, and you're not holding on to the handle. And then all of a sudden the driver of the bus slams on the brake. What happens? Well, the bus stops, but your body, because it has inertia, it keeps moving forward. And it keeps moving forward, continuing the motion that it previously had. So that's what I mean. An object in motion remains in motion. So inertia is related to mass, but not equal to mass. Although, the higher the mass, the higher the inertia. The higher the mass, the harder it is to change an object's motion. Okay? Now, this other part here that I already wrote, the second line, this is actually Newton's second law. Oh. I'm just going to write second law, but it's Newton's second law. Okay? And Newton's second law is basically exactly opposite of the first law. And it says that unbalanced forces change motion of the object. An object. Okay, this one actually has a mathematical equation. Sum of all forces equals mass times acceleration. Now remember, in the beginning I told you that F equals ma is bad, right? It is. This is the correct version of that statement. It's not any force that can be written as mass times acceleration. It's specifically net force, sum of all forces. Only sum of all forces, and only if that sum ends up not being zero, only that can cause change in motion as an acceleration. That's one reason why that equation on the right is wrong. The other reason is that equation makes no reference to vectors. And we know that forces and acceleration are vectors. So if we're going to write a law, we need to write it properly. Okay, so see how first and second law are kind of backwards of each other? So if the forces are balanced, there is no acceleration. If the forces are unbalanced, there is acceleration. This law is sometimes called law of cause and effect. Okay? So the net force is the cause, and the acceleration is the effect. Okay? We'll also be using this equation quite a bit in this class. And finally, third law. So third law is called law of action and reaction. Law of action and reaction. In simple terms, this law says for every action, there is an equal and opposite reaction. Of course, when we say action and reaction, we mean forces. For every action force, there is equal and opposite reaction force. A slightly more involved definition would say something like this. When two objects, any object, are interacting, they exert equal and opposite forces on each other. When two objects are interacting, then they exert equal and opposite forces on each other. So the word equal refers to magnitude. So I could write it like this. Force that object 1 exerts on 2 is equal to force that object 2 exerts on 1. This is another way to refer to forces. So if you have many objects, to identify what's going on with each one of them, you could use subscripts like this. So force 1 on 2 is equal to force 2 on 1. So this is a scalar equation, only with magnitudes. And if I want to make this into a vector equation, I would write it like this. So the negative sign also means opposite, right? So this is the vector equation. So the two forces that the two objects exert on each other are equal in magnitude and opposite in direction. So for example, if you have two objects, by the way, this doesn't have to be just contact forces. It could also be non-contact forces as well. If you have two objects in direct physical contact, so let's number them, 1 and 2. Object 1 exerts a force to the right on 2, and object 2 exerts equal and opposite force to the left on object 1. So every time that there is a contact between two objects, there is immediately a pair of forces. Sometimes we even call these guys action-reaction pair. I usually shorten it to AR pair. Okay? Now, in English, probably other languages too, it kind of sounds like action happens first and then reaction happens later. But that's not the case. So as soon as there is contact, right now we're just going to concentrate on contact forces. The two forces, the action-reaction forces, are instantaneous and simultaneous. So as soon as there is contact, the pair of forces is there. So it has absolutely nothing to do with, let's say, free will or anything else of the sort. Like, for example, I can say, I'm a human, I have free will, I can walk to the wall and touch it. Well, it sounds like I am the one who chose to walk to the wall. I am the one who chose to come in contact with the wall. So it sounds like that the force that I'm exerting on the wall is the action force. But that's not the case. So as soon as that contact is there, I can say I am exerting a force on the wall. Force of Daria on wall. But I can also say that the wall is exerting equal and opposite force on Daria. So it doesn't matter, quote unquote, who started it. There is no such thing as who started it in physics. As soon as there is contact, the two forces are instantaneous and simultaneous. So it doesn't matter which one you call action, which one you call reaction. Okay, so that's an intro to forces. It's probably the longest lecture that we've had to this point. We're obviously going to do a lot more with forces during the semester. In the next set of lecture notes, I will show you how to identify forces, how to draw a free body diagram, and how to figure out if those forces end up being balanced or unbalanced, and what exactly that means in terms of subsequent motion of that object.